You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Logic and reasoning form one of the oldest and most enduring foundations of artificial intelligence. While modern AI often emphasizes data-driven methods like machine learning, logic-based systems remind us that intelligence also involves structured reasoning. Logical reasoning enables AI to derive conclusions from facts, rules, and relationships in systematic ways. It is not about guessing or pattern recognition, but about following consistent rules of inference. For example, given the statements, "all mammals are warm-blooded" and "whales are mammals," an AI system using logic can deduce that whales are warm-blooded. This step-by-step reasoning mirrors how humans use logic in arguments and problem-solving. By formalizing these processes, AI systems can move from raw data to new insights, ensuring consistency and rigor in their decisions. Propositional logic represents the simplest form of logical reasoning, where knowledge is encoded as statements that are either true or false. These statements can be connected by logical operators such as and, or, and not to build more complex expressions. For example, the propositions, "it is raining" and "I have an umbrella" could be combined to represent "it is raining" and "I have an umbrella." Propositional logic provides clarity and precision, making it useful for systems that require absolute truth values. Its simplicity, however, also limits its expressive power. It cannot easily represent relationships, quantities, or generalizations, which are essential for more complex reasoning tasks. Nevertheless, it serves as the entry point for logical reasoning in AI. Predicate logic, also known as first-order logic, extends propositional logic by introducing quantifiers and variables. This expansion allows AI systems to express richer and more flexible knowledge. For example, the statement "all humans are mortal" can be represented using universal quantifiers, while there exists a student who studies AI uses existential quantifiers. Predicate logic captures relationships between objects, enabling reasoning about categories, properties, and interactions. This expressiveness makes it suitable for domains like legal reasoning, scientific modeling, or natural language processing, where complexity cannot be captured by simple true-false statements alone. For learners, predicate logic represents the bridge between simple logic and the broader, more nuanced reasoning needed in real-world applications. Deductive reasoning is one of the core logical processes AI systems employ. Deduction works from general rules to specific conclusions. For example, if the rule is "all birds can fly," and we know that a robin is a bird, then deductive reasoning leads to "robins can fly." This type of reasoning ensures certainty as long as the premises are correct. Deductive reasoning has powered many expert systems and rule-based approaches in AI, offering a transparent and reliable way of making decisions. However, its reliance on complete and accurate rules can also be a limitation, as real-world contexts often involve uncertainty, exceptions, or incomplete information that deduction alone cannot handle. Inductive reasoning works in the opposite direction, moving from specific observations to general rules. For instance, observing that the sun has risen every morning so far might lead to the generalization that the sun always rises in the morning. In AI, inductive reasoning underlies many forms of machine learning, where patterns in data are generalized into predictive models. Unlike deduction, inductive reasoning does not guarantee certainty. Its conclusions are probable, rather than absolute. Still, it is a powerful tool for dealing with incomplete or evolving knowledge. For learners, induction demonstrates how AI systems can generate rules dynamically using evidence and experience rather than relying solely on predefined laws. Abductive reasoning adds another dimension by seeking the most likely explanation for observed evidence. It is often described as, quote, inference to the best explanation. For example, if an AI system detects wet grass in the morning, it might infer that it rained overnight, even though other explanations like sprinklers are possible. Abduction is valuable in diagnosis and hypothesis generation, where certainty is elusive but plausible explanations are needed. Medical reasoning systems, for instance, often rely on abduction to propose likely causes of symptoms. This form of reasoning highlights the practical side of intelligence. In many real-world situations, we do not seek absolute truths, but the most reasonable explanations based on available evidence. Rule-based expert systems illustrate how logic has been applied in AI to capture human expertise. These systems consist of large collections of if-then rules derived from domain experts. For example, an engineering system might contain rules like, if the temperature is above threshold and pressure is high, then shut down the system. When combined with inference engines, these rules allow machines to mimic expert decision-making. Expert systems were especially influential in the 1980s, proving effective in fields like medicine, engineering, and finance. Their transparency made them easy to interpret, but their rigidity and reliance on extensive human input also exposed their limitations. Still, they remain an important milestone in the history of AI. Inference engines act as the reasoning core of logic-based AI systems. They apply logical rules to knowledge bases, deriving new conclusions from existing facts. An inference engine might use deductive methods to expand knowledge systematically, or heuristic methods to focus on promising paths. For instance, in a medical expert system, the inference engine links symptoms with potential diseases by applying the relevant rules. This process transforms static data into actionable insights, enabling AI to function as a problem solver rather than just a fact retriever. Inference engines embody the dynamic aspect of logic in AI, showing how machines can reason by methodically extending knowledge. Forward chaining is a reasoning strategy that begins with known facts and applies rules to derive new conclusions step by step. It is often described as data-driven reasoning. For example, given the facts, the patient has a cough, and the patient has a fever, forward chaining may trigger rules that lead to a diagnosis. This approach is useful in environments where facts are abundant and multiple rules may apply simultaneously. Forward chaining illustrates how AI systems can expand their knowledge incrementally, building from observations toward outcomes without needing to know the goal in advance. Backward chaining, by contrast, is goal-driven reasoning. It starts with a desired conclusion and works backward to determine what facts are needed to support it. For instance, if the goal is to diagnose pneumonia, the system identifies the conditions required for that diagnosis, such as fever, cough, and chest pain. It then checks whether these conditions are present in the knowledge base. Backward chaining is efficient when goals are clear and focused, reducing the need to explore irrelevant information. Together, forward and backward chaining illustrate complementary strategies in reasoning, each suited to different problem-solving contexts. Non-monotonic logic introduces flexibility by allowing conclusions to change when new information is introduced. Traditional logic is monotonic, meaning once something is concluded, it remains true regardless of new facts. But in reality, knowledge often evolves. For example, we might infer that birds can fly, but must retract that conclusion when learning about penguins. Non-monotonic logic enables AI systems to handle such revisions gracefully, reflecting the fluidity of real-world reasoning. This adaptability makes systems more robust and realistic, though also more complex to implement. For learners, non-monotonic reasoning highlights the challenge of designing systems that can change their minds when the world proves them wrong. Default reasoning offers another strategy, where AI systems assume typical conditions unless evidence suggests otherwise. For instance, a reasoning system might assume that birds can fly as a default, but override this assumption when encountering exceptions like penguins or ostriches. This approach reflects how humans often reason, making assumptions in the absence of complete information. Default reasoning allows systems to act efficiently without requiring exhaustive data for every situation. However, it also introduces risks of error if defaults are applied too broadly. Understanding default reasoning illustrates the balance AI strikes between efficiency and accuracy in everyday contexts. Probabilistic reasoning combines logic with probability, allowing AI to handle uncertainty systematically. For example, instead of concluding definitively that the patient has flu, a probabilistic system might say there is a 70% likelihood of flu given the symptoms. Bayesian networks exemplified this approach, linking variables in probabilistic relationships that can be updated as new evidence appears. Probabilistic reasoning is vital in domains like medicine, finance, and security, where decisions must often be made under uncertainty. By blending logical structure with probabilistic inference, AI systems achieve both rigor and realism, approximating the way humans balance evidence and uncertainty in decision-making. Fuzzy logic systems represent another extension, reasoning with degrees of truth rather than binary values. Instead of declaring that the temperature is hot or not hot, fuzzy logic allows expressions like the temperature is somewhat hot. This approach is useful in systems where precision is impractical or unnecessary, such as climate control, washing machines, or decision support. Fuzzy logic mirrors human reasoning, which often operates in shades of gray rather than absolutes. By accommodating imprecision, fuzzy systems enable AI to function effectively in environments where crisp boundaries are unrealistic. This flexibility expands the range of problems AI can address, bridging the gap between rigid logic and real-world nuance. Despite their strengths, logic-based AI systems face significant challenges. They can be brittle, struggling with exceptions or incomplete information. Scalability is another issue, as maintaining vast rule bases becomes complex and computationally demanding. Interpretability, once a strength, can also become a weakness when rules grow too numerous or intricate for humans to follow easily. These challenges explain why purely logic-driven systems have been supplemented by probabilistic and learning-based approaches. Yet the persistence of logic in AI research demonstrates its enduring value. Logic provides clarity, transparency, and formal rigor, even if it must be balanced with flexibility and adaptability in modern applications. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Logic plays a central role in natural language processing, where systems must parse sentences, interpret meaning, and answer questions. Understanding language requires more than recognizing words. It requires reasoning about relationships and implications. For example, a system asked, "Who is taller, Alice or Bob, if Alice is taller than Bob?" must rely on logical inference to provide a correct answer. Logic helps structure grammar, resolve ambiguities, and connect statements to broader knowledge bases. While statistical methods dominate much of modern NLP, logical reasoning ensures consistency and coherence, especially in tasks involving complex queries or formal domains. For learners, this demonstrates how symbolic reasoning continues to complement pattern recognition in AI's handling of human language. In robotics, logic provides the framework for planning and executing tasks. A robot tasked with cleaning a room might use logical rules to ensure that if the floor is dirty, then vacuum it, or if an obstacle is detected, then navigate around it. These rules allow robots to move beyond raw sensor data, reasoning about goals and conditions to act purposefully. Logic also enables coordination, ensuring that sequences of actions fit together coherently, such as fetching tools before starting a repair. This structured reasoning transforms robots from simple machines following fixed routines into adaptable agents capable of planning in dynamic environments. Logic ensures that robotic actions are not random but directed by consistent principles. Legal reasoning provides a particularly vivid application of AI logic. Laws, contracts, and compliance requirements are essentially collections of rules and conditions, making them well suited to logical analysis. AI tools can represent statutes as logical rules, then apply inference engines to analyze cases, detect conflicts, or check compliance. For example, a system might assess whether a contract violates regulations by systematically checking clauses against legal requirements. The interpretability of logic makes it attractive in law, where transparency and accountability are critical. Yet the complexity and ambiguity of human legal systems also highlight the challenges of encoding nuanced reasoning into rigid structures. This application shows both the potential and limits of logic in AI. Medical reasoning systems have also long relied on logical frameworks. Diagnostic systems such as early expert systems encoded medical knowledge into rules linking symptoms with conditions. Given patient data, the system could infer possible diagnoses and recommend treatments. Logic provided a clear and explainable reasoning trail, allowing physicians to see why the system reached a conclusion. While statistical and machine learning methods now dominate, logical reasoning remains valuable in contexts where interpretability and reliability are essential. Medicine underscores that logic is not just an academic exercise. It can directly influence human lives, making its transparency a crucial strength in sensitive domains. Modern AI increasingly embraces hybrid systems that combine logic with machine learning. Symbolic reasoning provides structure and interpretability, while data-driven learning offers flexibility and adaptability. For example, a hybrid system for legal analysis might use machine learning to extract clauses from documents and logical rules to evaluate compliance. This combination addresses the brittleness of pure logic and the opacity of pure learning, creating systems that are both powerful and trustworthy. Hybrid systems illustrate a broader trend. Rather than viewing logic and learning as competing paradigms, researchers recognize their complementarity. Together, they move AI closer to flexible, human-like intelligence, capable of reasoning and adapting simultaneously. Knowledge graph reasoning represents a powerful modern application of logic. In a knowledge graph, entities such as people, places, or concepts are linked by relationships. Logical inference allows machines to traverse these graphs, discovering new connections. For instance, if a graph states that Paris is in France and France is in Europe, a reasoning system can infer that Paris is in Europe. This ability to extend knowledge systematically underpins search engines, recommendation systems, and digital assistants. Knowledge graph reasoning demonstrates how logic enhances interconnected data, turning vast webs of facts into actionable insights. It is a vivid example of how symbolic reasoning supports practical, large-scale AI applications. Bayesian logic models blend probability with logical structure, enabling reasoning under uncertainty. While logic provides the framework of rules and relationships, probability accounts for incomplete or noisy information. For example, a Bayesian logic system might represent that if a patient has a fever, there is a 70% chance of flu. This fusion allows AI to reason in complex, uncertain environments while retaining structure. Bayesian logic models illustrate how traditional boundaries between logic and probability have softened, creating hybrid systems that mirror the probabilistic reasoning humans often use. They embody the ongoing effort to make AI reasoning both rigorous and realistic. Temporal logic introduces reasoning about time, enabling AI systems to handle events and states that evolve. Unlike static logic, temporal logic can represent sequences and conditions across time. For instance, if the light turns green, then eventually the car will move, captures cause and effect relationships unfolding over intervals. Temporal logic is crucial in domains like robotics, scheduling, and verification of software systems, where the order of events matters. It reflects the reality that intelligent behavior is not just about static facts, but about processes unfolding dynamically. For learners, temporal logic highlights how reasoning must extend beyond snapshots into continuous flows of action. Modal logic extends reasoning further, incorporating notions like necessity, possibility, belief, and knowledge. This framework allows AI systems to represent not just what is true, but what could be true, what must be true, or what an agent believes to be true. In multi-agent systems, for example, modal logic can represent differing beliefs among agents, enabling richer interactions. While more abstract than propositional or predicate logic, modal logic aligns closely with human reasoning about uncertainty and perspective. It expands the scope of AI reasoning beyond hard facts into the more nuanced realms of possibility and subjective knowledge. Ethical reasoning in AI attempts to encode principles of fairness, responsibility, and moral choice into logical frameworks. For example, a self-driving car might be guided by rules such as do not endanger pedestrians or prioritize minimizing harm. Encoding ethics in logic allows systems to make decisions transparently, enabling humans to examine and adjust their principles. While highly challenging, these efforts reflect the recognition that AI systems increasingly face choices with moral consequences. Logical structures provide one way to formalize these decisions, though they also raise deep debates about whose values are represented and how they should be prioritized. Transparency is one of the strengths of logic-based reasoning systems. Unlike deep learning models that function as opaque black boxes, logical systems make their reasoning explicit. Each conclusion can be traced back to specific rules and facts, providing accountability. This transparency is invaluable in contexts like law, healthcare, or finance, where stakeholders need to trust and verify AI decisions. However, transparency does not guarantee usability. Large rule bases can become so complex that human users struggle to follow them. Still, the principle of interpretability distinguishes logical reasoning from purely statistical approaches and ensures its continued relevance in critical applications. Advances in automated theorem proving showcase the power of AI reasoning at the frontier of mathematics and logic. These systems can prove the validity of logical or mathematical statements automatically, exploring proofs far beyond what humans could manage by hand. Automated theorem provers have been applied in software verification, ensuring that programs behave as intended, and in formalizing mathematical discoveries. They exemplify how AI can extend human intellectual capabilities, tackling problems that require both rigor and scale. For learners, theorem proving demonstrates the precision of logic applied at its highest levels, showing how structured reasoning can achieve remarkable results. Despite advances, computational complexity remains a major challenge in reasoning systems. Some logical problems are provably intractable, meaning they cannot be solved efficiently with current methods or resources. The more complex the knowledge base and rules, the more computational effort is required. This limitation explains why purely logical approaches often falter at scale, giving way to probabilistic or hybrid methods. Complexity underscores that reasoning, like search, must balance completeness with feasibility. It reminds learners that while logic provides clarity and precision, its power comes with computational costs that must be carefully managed in practice. Reasoning systems also play a key role in intelligent agents operating in complex environments. Agents rely on logical reasoning to interpret conditions, set goals, and plan actions. For instance, a personal assistant agent may use rules to prioritize reminders, schedule tasks, or manage conflicts between obligations. In robotics, agents reason about constraints, such as, if battery is low, then return to charging station. Reasoning transforms agents from reactive machines into proactive, goal-oriented systems. By applying logic, agents demonstrate autonomy, making choices that align with objectives while adapting to changing contexts. This shows how reasoning supports the broader vision of AI as intelligent action. Looking to the future, research in logic and reasoning is increasingly focused on combining symbolic and sub-symbolic approaches. Symbolic reasoning provides clarity and structure, while neural networks offer adaptability and scale. Together, they promise systems that can reason formally while learning flexibly from experience. This integration could address the brittleness of logic and the opacity of learning, producing AI that is both explainable and powerful. For learners, this trend highlights the enduring relevance of logic in AI. Even as machine learning dominates headlines, reasoning systems continue to evolve, ensuring that logic remains a vital part of building truly intelligent machines. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.